from like half. I don't know.
I don't need to.
Okay.
I don't need to.
Give me like 2 minutes. I'm almost done with this setup. This live streaming thing makes no sense to me.
So you do it that way.
Okay.
Then you do the base case first. Never do that double sign curve. You don't want that double sign. So this one you can do zero because it's already. Don't worry about the cache. Look at the water. Now, if you don't have more air on, you have to.
Let's start with this setup. Oh, it worked. Okay, perfect. Let's turn this off. Then we will begin with this. Okay, let's see. Capture.
You have you eating. If you do R minus 1, you need to eat it. That means you have to add the profit of eating.
Oh, there's something.
This step you only do eat or you skip. This is, looks like the eat. So that means what is the grade? What is the this one here? This one, the 1, 4, 2.
Okay. Are you leaving? Thanks for your help. We're huge help to this contest. Did very well. See you later.
Let me know if you need any help.
Sure. Does this work? Please work.
Because you skip. So in here, what is the basically you're talking what is the best? Which one should I take?
All right. I think it's working. Hello.
Something I should add to Henry the Magician.
Hats on his feet. Let's begin. I'll put this one here. So how about we start with a problem review with Max Multiset the first. Max Multiset A is a problem that becomes pretty simple if we just take a look at one very interesting idea. So how about we take a look at the input set for this one? This array has -3, 2, and 2, and the output is 4. Let's take a look at this one. -1, -5, and they're all zeros. Then 10, 5, -2, 4, 9, -13. Is there a pattern which we can get from this input to the output? There's a very, very easy pattern we can take a look at. Do any of you guys know it? Yeah?
Just sum all of the numbers that are positive.
Just sum all the positive numbers, right? Yeah, that's a pretty simple first problem. So we're just gonna write a program to take in that input and add together all of the numbers that are positive. All we're gonna do is to do this. I'm gonna write this in Python because it's fast and most people know Python, I'm guessing. Most are Python people, yeah? We're gonna start with just input. That is going to get the first line of input. This 6 is gonna be how many things are in the list. Python though, we don't really need the first number because Python lets us easily turn this one into a list just with this. Array equals list map int input dot split. This makes no sense, right? Let me break down this code. Input is going to get me this line of input, or the second line of input in the code. The reason it's not going to give me the first is because it's going to skip the first line of input with this input. Second line of input is going to be do with this one. Split is going to split it up. So it's going to end up being an array of 0, an array of 10, 5, -2, 4, 9, and -13. But those are still going to be strings. Those aren't yet integers. We have to map each of those ones into an integer before we can actually do the problem. To do that, we call the map function, which takes in the function to map everything with, and then the list. So this ends up mapping everything from the string array into an array of ints. Last, we have to wrap that with list in order to turn it into a list where we can use. At the very end, if we print the array, this will end up with the array. just like this. These are all numbers. If we didn't have this map stuff, we would end up with a list of strings, which is not what we want. These are all strings. You can see the quotation marks around it. Now that we have this array, we have to run through the array and add together every element that's positive. To do that one, all we need to do is to do a for loop for every element in array. Alternatively, you can do something like for I in range length of the array. These are pretty much the same thing, but this one just gets you the I, the index. We don't care about the index for this one, so I'm going to use the first method, the enhanced for loop. We're going to say, as long as the number is positive, we're going to add it to a sum. I like to call it total. I'm going to start it off at 0. I'm going to say, if that e is bigger than 0, we're going to add that to the total. At the very end, we print out that total. Let's give this one a try. There we go. This is the first one, max multiset A. Oops, that's leaderboard. How do I go back to the problems? Max multiset B is definitely a tougher one. I talked to many of you people, and we were starting off sorting very good. So the problem for this one is that same as multiset, it's very similar to multiset A, where you want to get the maximum one, but we're given a length of the multiset. So you have to get a multiset with that given length. Since we are looking for the maximum elements, it's optimal to sort it first and then pick the biggest elements just by going through the list. So let's do it like this. I'm going to first start by getting the first two numbers, length and queries. This 8 just means how many things are in this array. This 5 means how many things we have down here, or queries, which means like I'm pretty much accessing that list. It's asking me something. Just like before, I'm gonna do a map and split it. That's gonna get me the length and the queries. Then I'm gonna get my array with the same thing I did before. Then I need to sort the array, but how about we try to sort it from biggest to smallest? Let's do it like this. Array.sort, we're going to set it to reverse equals true. And let's see what we've got. 5, 4, 2, -1. 1, if we take a look at these queries, 1 pretty much, we're just looking for the multiset with a length of 1, which is going to give me the maximum. That's just going to be 5, right? It's going to be the biggest thing in the list, the very first thing. If we go 3, that's going to be the first 3. And we're just adding these together, right? We're adding these together. And 0 means we're not selecting any elements. We're just going to return a 0 for this one. So we're going to do it like this. 4. We're just going to loop through the queries. I'm going to set my current query to the input. And then we're going to do it like this. Total equals 0, just like we did before. For I in range of that query, we're going to do total plus equals array at I. At the very end, print out the query. Print out the total. Give this one a try. It's going to fail because I forgot to comment out this one, but it looks like it's getting me the correct answers. There we go. Let's give this one a try. If I submit it just like this, it's going to pass the sample inputs, but unfortunately, it's not going to pass the whole inputs. The reason it's going to time out on these, terminated due to timeout, is because this is a double for loop. This is looping. Let's say my length of the array is length 100,000. And let's say each of my queries are also 100,000. That's not going to be very ideal if we're looping 100,000 times. It's going to end up being 10 to the 10th power number of accesses. That's not good. That's not very fast. We can speed this up if we use a technique called the prefix sum. Let me explain that one. Let's see. How about we start with what we had before, with the array of 5, 4, 2, and -1. Our queries previously were 1, 3, and 0, which would give us 5, 11, and 0. Our code, how we were running the code before, is that we were just doing this loop, and we're just going to loop this number of times. 1 means we're looping from 0 all the way to 1. We're just getting 5. 3 means we're looping 1 indexes 0 through 2. 0 means we're not looping through any of them. We're just adding, resulting in 0. The problem with this one is because we're looping twice, that does put a huge strain on the computer, makes it very, very slow. We can speed this up if we can pre-process this array and get all of those sums beforehand. This is where the prefix sum comes in. I'm going to set this to my array equals this one, and I'm going to make another array called prefix. I'm just going to start it off as a 5 and some trash values, something like a 0, 0, 0, something like that. To actually fill in the prefix sum, let's think about it like this. We can say, and the whole point of the prefix sum is to make querying from a range very, very easy. This will be explored more in Max Multiset Sum 3. But for now, I'm going to move, let's see, how do I select this stuff? Let's move this one over a little bit more. That's cool. How do I move it? Oh, come on. Let's think about it like this. 5 is then going to be the sum of 5 and nothing. Because how this prefix sum works, that each of these indexes is the sum of every array, every number in the array prior to that index. So this index 0, 1, 2, and 3. If we take this index 1, it's going to end up being 9, because 9 is the sum of 5 and 4. If we take this 2, it's going to be 11, because 11 is the sum of 5, 4, and 2. Finally, 10 is going to be the sum of 5, 4, 2, and 1. We can generate the prefix sum pretty simply if we just run a double for loop. But again, we're trying to avoid a double for loop. So we don't want to do it like that way. How do you think we can generate this prefix sum if we're in O of n time and not using a double for loop? You guys have any ideas? Yeah?
You take the previous sum and just add the next number to it.
That's right. So how this one, what he's saying is that each number in the prefix sum is the sum of the previous elements. Like this one, 5 is just 5. 1 is going to be 5 plus 4, which is going to be 5 plus 4 plus 2, and 5 plus 4 plus 2 plus 1. This is just how we would do it in a double for loop. When we fill in 4 for this one, when we fill in 9, this 9 is just a sum of this number and this number. But we can also think of this one as a sum of this number and this number. So we can think of it as like crossing together, and that's going to be the next elements. 2 is a sum of 5, 4, and 2. This is the sum of 9 and 2. Because 5 plus 4 plus 2 is just a sum of this plus 2. There's like a 5 plus 4 plus 2 plus -1 is a sum of this plus this. So we can use the previous values in the prefix sum to compute the next values. In O of n time, it's going to end up being 11, because the sum of 9 and 2 is going to be 11. 11 and -1 is going to end up being 10. That's going to be our prefix array. How we code this, let's take a look, is we're going to start off with just the previous code. Instead of doing this stuff, this is the stuff that was really killing our time. This is just too slow. We're going to pre-process this one to get the prefix sum first. I'm going to start my prefix sum as a bunch of zeros by the length. So at the very start, prefix is going to be just a bunch of zeros. We can see that if we print out the prefix. I'm going to set prefix, the very first element, to the first element of the array. Then we're going to do the for loop. For I in range, we're going to start at 1 this time to the length. We're going to do prefix at I is the sum of the previous element, prefix at I minus 1, the previous thing in the prefix sum, plus array at I. Then we'll try to print it out again, see what happens. And let's see what this one prints out. It's going to fail, since we don't actually have the correct output, but you can see it's going to start off as 5000, then we're going to fill it into 5, 9, 11, and 10. Once we've got that, all we need to do is to access the elements at this index minus 1. So 1 is going to end up being index 0. 3 is going to be end up index 2. 0 is a tough case. It's going to be 0 minus 1, which is negative 1. In Python, that'll go to 10. But if it's a 0, we're just going to print out 0. So we're going to do like this. We're going to do if that query equals 0, we're just going to print out 0. Otherwise, we're going to print the prefix of query minus 1. Let's see what this one does. 5, 11, and 10. And this one will pass because this one's time complexity is not going to be a double for loop. Instead, it's going to be O of nlogn because of this sort. Much, much better improvements. Let's take a look at Multiset 3. Just like Multiset B, it is a prefix sum problem, but it combines more of Multiset A, the concept, than Multiset B. Because in this one, we are given a range, and we have to print out the maximum multiset of that subarray. 2, 3 means I'm printing out the maximum multiset from the indexes 4 and 1. So we take this array, then we find the maximum multiset from it. 1 and 4, we take this array, find the multiset. 0, 0, we take this multiset. This subs array is just a negative 3, and find the multiset from that. Just like what I said here, 4, 1 is from 2 to 3. 1, 4 is going to be from negative 1 to 5, like I have here. 0, 0 is going to be negative 3. Note that this is inclusive, so I have to include that one. So let's take a look at this one. Just like Multiset A, the trick for this one is that the maximum multiset is the subarray, is the multiset with no negative numbers. So we're going to ignore every negative number. But let's start by trying to put this one inside this thing. Just like before, we're going to use a prefix sum. Negative 3, negative 1, 4, 1, 5. And how about we just, let's see, what if we scroll down here? So negative 3, negative 1, 4, 1, 5. Then we have to find, let's say we're going from, oops, where's my mouse? There it is. Oh, it's gone again. Wow, I can't see my mouse, this is hard to draw. 4, 1, let's say we have that. If we have this, then we're going to be able to get the multiset from this. But just like before, we're going to use the prefix sum to speed this one up a lot. How we're going to do this is we're going to compute a prefix sum of this entire list with a little twist, because we're going to ignore every negative number. If our array is negative 3, negative 1, 4, 1, 5, we're going to build our prefix sum like this. We're going to do prefix. This is going to start at 0, actually, for this time. Equals just an array of 0 multiplied by the length of this one. This is going to be, I usually like to make my prefix sum starting at 0. There are different ways to do this one. This is my preferred way, and I will explain why later. But we're going to do something a little bit different for this one. For I in range of that length, wow. Of course, it's going to be my array. It's going to be my prefix. We're going to only add onto the prefix if the element is positive.
Hey, I'm going to take off.
Sure, sounds good.
So just make sure everything, this room's locked up
Okay,
and that area's clean.
sure, sounds good. Thanks for your help. So for everything inside this length, we're going to say if, let's start by doing this actually. This element is going to be array at I. It's going to be my current element from here. I'm going to say if my E is positive, then we're going to do just like we did before with the prefix sum. Prefix at I equals prefix I minus 1 plus E. But what if it's negative or 0? Are we still going to add it to the prefix? This is a trick question. We're not going to add E to the prefix, but we still have to expand the prefix sum because we still have to go through the length of the array. So we're just going to do prefix at I equals prefix at I minus 1 with no plus E. The reason we have to still add it is because our prefix sum does have to match the length of the array. It does have to have every index in the array covered, even if we're not actually changing it. If we generate the prefix sum for this array, it'll end up being -3, -1, 4, 1, 5 is our original. Our prefix sum is actually going to start, let's see, how do we do this one? And I'm going to do something a little bit different with this prefix sum. I'm going to do prefix of I plus 1 for the prefix sum, instead of an I minus 1 over here. I plus 1, I plus 1. I'm making this prefix sum shifted to the right by 1 element. It's going to start off at 0, and then we're going to start generating the prefix sum. So we're going to go through every element in here. We're going to say, is this positive? No. We're going to add to the prefix sum this element just by itself. This is also negative number, so we're going to add another 0. 0, I'm not adding a 0 every time, but this 0 just means the previous element is the same as the previous element. Now once you get to a 4, we see it is positive, so we're going to do 0 plus 4 is going to be in here. 1 is going to be 4 plus 1, going to be 5. 5 is going to be 5 plus 5, which is end up being 10. Now that we have this prefix sum, we can use this to pretty quickly calculate the sum range. Let's say my current query is 2 and 3. So we're pretty much getting this subarray. We're getting the subarray from 4 to 1. What we're going to do, and I'm going to put the indexes here as well, 0, 1, 2, 3, 4, 5. A huge advantage of the prefix sum is the ability to compute ranges, the sums of a range, instantly. We can think of the prefix sum. What we did before is 0 to that number. But we're, in this question, thinking of going from the left index to a right index. 2, 3 means we're pretty much going from index, let's see, index 4 minus index 2. That's going to give me a 10. The reason we're going to do this is the logic of like, think of it as a number line. 0 through 4 minus the sum of 0 through 1 turns out to be these numbers. Sorry, the sum of 0, let's see, 0 through 1 turns out to be this thing. So I'm going to do the example on this one actually, is a little bit better to see. But the sum of 4 to 1 is the sum from, the sum from 2 to 3 is the sum from 0 to 3 minus the sum from 0 to 1. So 2 to 3 is the sum from 0 to 3 minus 0 to 1. Does that make sense? Anyone have a question on that?
Yeah.
Yeah?
Christian, why is the, why do we make negative number? Like, why don't we want negative? Why don't we make it 0?
I did a plus 1 over here. Because my I is starting at 0, then prefix of I minus 1 over here is going to go out of bounds.
Which that's why we make the negative 3 into 0.
Why we put the -3 into 0? Yeah. So we're looking for a prefix sum that pretty much ignores negative numbers. Just like Max Multiset A, remember how we ignored the negative numbers?
Oh, okay.
This one is also going to ignore the negative numbers, but it's as a range, so it's very interesting. Yeah. So to get the sum of 0 to 3, it's just going to be the prefix sum at 4, at the number plus 1, pretty much. To get the sum from 1, ignoring the negative numbers, it's going to be at 2. So it's going to be pretty much left plus 1, right plus 1. I have to be a bit careful though, because this one's going from 4 minus the prefix at 4 minus the prefix of 2. Wow, what's going on here? If my numbers are 2 and 3, I'm going to say my L equals 2, right is 3. It's going to be prefix of right minus prefix of L. Because prefix of R pretty much means the sum of the array from 0 all the way to 0 all the way to 3. And L is going to be the sum from the prefix sum from all the way from 0 all the way to 1. So it's going to be this whole thing minus this thing, but as a prefix sum, so it's instant. This will make more sense when I code it. That was a very confusing explanation, but let's code this one here. Just like before, we're going to do length queries. Wow, that was bad. And we're going to do then my prefix sum for loop I in range length prefix E is going to be array at I if E is greater than 0. If it's greater than 0, we're going to add it to the prefix. The else case, we're going to do prefix I plus 1 equals prefix at I. And let's see what this one prints out. Pretty much this one's just the same thing, but it's same as before, but we're ignoring every negative number. If we encounter a negative number, we don't change the prefix sum, pretty much. This will make more sense the second test case, where I say I'm adding 2 here. Is it 2? I'm adding 3. But I'm not adding a -5. I'm ignoring the -5 and it's saying exactly the same. So pretty much this is just going to keep increasing, even though it might decrease over here. Yeah?
Why do we start with 0?
Why do I start with a 0 over here?
Yeah. Well,
I'm just more used to it this way. You can start it with, like the logic's going to be the same. It's going to be the same idea, even if you don't start it at 0. I just prefer it this way because I'm more used to it. You can totally make it work if you don't start it with a 0, though. We're into the prefix. And then we're going to do, for every query, we're going to do left and right. We're going to do print prefix at right plus 1, prefix at L. Let's see. And you guys can see, although the logic might be a bit tough, the code is not too bad. All this one is a for loop, arrays, an if, another for loop. That's not too bad at all. You guys know this code. It's just the process of putting it all together and getting the code from it. And the logic is the tough part, which we'll have to get used to by lots of practice. But the little building blocks of the code are not too bad. Integral is a bit of an interesting one because there are just a ton of instructions, even though the concept itself is not too bad. The idea of this one is that we parse this array and then get the integral of this one. Everything here is explained in the instructions, but let's go through this instruction with a -2, 0, 1, and -5. This turns out to be this array, as stated in the input. And it is good to take a look at the explanations if there are any. This is very good to just learn from, see how the writer of the code does it, writer of the problem does it. We're converting this array into the number here is -2, which is our coefficient of the array, of the term. The index of this one is 0, which becomes the power. Coefficient is 0, index is 1, 0x to the power of 1. Element is 1, element is 1, index is 2, 1 times x to the power of 2. Elements is -5, index is 3, -5 times x to the third. So pretty much just turning this into this polynomial and then taking the integral. First step of taking the integral, at least for polynomials, is going to be increasing each of these powers. So this is going to be 1, a 1, a 3, and a 4 from 0, 2, and 3. A 0, 2, and 3 becomes 1, 3, 4. Then, yep. Oh, is that a question, you guys? Oh, okay then. Oh, good. And then we're going to divide each coefficient by that power. So -5 divided by 4, 1 divided by 3, -2 divided by 1. At the very end, all we need to do is plug in the bounds, which is going to be 3 and 1 in this case. Subtract these two results, and then return this as our final answer. So let's do that one. Let's give the first line of input because Python is built different. Polynomial is going to become this list map int input dot split. Left, right is going to be map like that. And then we're going to have to do the tough part. We need to loop through everything inside here to compute the result. We're going to start doing like this. For power in range, for I in range of, no, I think I do this one. Length. But we do like this. We're going to put power is going to be that I plus 1, because for each one of these, we're increasing the power by 1, just to state it in the instructions. Coefficient of the integral is going to be the term divided by the power. It's going to be my polynomial at I divided by the power. I'm going to do L sum for left sum, right sum for right sum. Then we have to add this to the left sum. Left sum plus or equals coefficient times, in this case our x is going to be our L to the power of power. You're leaving? I'll see you later then. Thanks for joining us. Congratulations. We're going to do the same logic for the right sum. At the very end, we have to print R sum minus L sum. It's going to get us this one. I will say this problem is mostly about just reading the instructions. And this is a tough one because there's so many instructions. To be honest, if I saw a problem like this during a contest, I might just skip it at first. There's too much reading to do, and programmers can't read, so it's hard. But if a problem has this, there's no shame in skipping problems, coming back to it later if you have time. But if it really is just too much reading, maybe the points just aren't worth it. Put your time into thinking of the problems rather than reading it, I would say. But it's not too bad if you understand it. All you need to do is follow the instructions here and submit it like this. And it should pass. There we go. Riemann sum is a tougher one because you will have to be careful of the floating point rounding error. And let me show you what I mean by that. Oh, my code is here. Bye. Just like before, we're going to start with the... Okay, well, I should explain the Riemann sum first. Riemann sum is another method, just like integral, for calculating the area underneath a polynomial or some kind of function. But it's not as precise, but it is easier, I would say. like easier as a concept. I don't know what came first, the Riemann sum or the integral, but what I do know is it's a pretty interesting problem. So let's do it like this. Riemann sum pretty much means you're drawing rectangles under the polynomial, summing up the areas to get an approximation of the final sum. Just like before, a polynomial is going to be this array, or our range is going to be this one. We also have to keep in mind how wide those rectangles are. The rectangles will have a width. So let's do it like this. Length, array, and this is all what I did before for the previous one. Then my left, right, and then my width. That's all the input parsing. Then comes the tough part. I'm going to start by doing a while loop. I'm going to do my cur x is going to be left. I'm going to start at, let's say for this one, 1. I'm taking the sum of the integral. Okay, well, how about we try to graph this one? Let's see. This is going to be 2x minus 1, right? So if we go over here and try to graph it, I'll make a new one, actually. Y equals 2x minus 1, Riemann sum from 1 to 3, with a width of 0.5. What that means is that if we draw this one out as a graph, I'm going to start at -1, go up by 2 every time, and this is just the, I don't know what kind of math is this geometry? I can't remember. And we're just drawing a bunch of tiny rectangles inside this one to approximate the area. I think this is called the left Riemann sum because the rectangles are stopping on the left top of it. Summing up the area of these ones will give us an approximation for the area under this curve. So area under this entire thing. How would we go about finding this y position? If we know x equals 0.5, sorry, if x equals 1, how do we go about finding this y position? Well, we can take x equals 1, plug it into the equation, and then solve for y. This is going to end up being y equals 1. We know this point, well, I drew it poorly, but it should be 1, 1. To get the area of this one, because this is a rectangle, it's going to have to be the height times the width, right? So a height equals 1. My width is always going to be 0.5 for this problem, because it's going to be your input. The area for this one is going to be 0.5. This is going to be, the second point is going to end up being when y equals 0.5, or sorry, when x equals 1.5. Because we're going to go up by the width every time. So when x equals 1.5, we're going to plug that one in. Y is going to be equal to 2. Height is going to be equal to 2. Width is 5. Then my area is going to be 1.0. We'll repeat that process for all the other ones. Add all those areas together to get the final result. If we do that code over here, it's going to look like this. Kind of similar logic as we did for the integral, except we're plugging it right into the array and not doing any of the fancy, what's it called? The adding the power, the dividing and stuff. So we're just going to do it like this. For while x is less than r, we're going to do a for loop. For I in range of AR. I do want to say this is a double for loop. If this is a double loop, this is generally not good. But the inputs, the constraints, aren't big enough where it's going to make much of a difference where you make a double for loop. This still runs fine. It all depends on the constraints. If these numbers are too big, avoid using the double for loop at all costs. But at this range, it's not too bad. Just depends. It'll come to you when you practice a lot more. You'll be able to guess that. For I in range length, I'm gonna do per height equals 0. Or just height actually. Oh wow. Height plus equals. Let's get the coefficient first actually. It's the array at I. And we're going to do height plus equals coefficient times x to the power of I. Because I, in this case, is our power. At the very end, we're going to do total area equals 0. We're going to do total area plus equals width times height, right? Width times height. The most important one is going to be x plus equals width. Oh, thank you. And then print out that total area. Let's see, does this work? Well, that's awkward. Yeah, there we go. There we go. Got one of them. The other one was wrong. What did I do? Oops. That's one I forgot about. It's going to be a float. Because the width of this one might be a 0.1, 0.5. Still not on this one. This is what I was worried about for this problem. There is, when you're working with floating point numbers, decimals numbers, you will encounter many rounding errors. Computers have limited precision. They cannot perfectly represent floating point numbers. Let me show you something actually. Let's see. What does it print out? That's not right, is it? Computers don't like floating point numbers. I don't like floating point numbers. I try to avoid them, but they have to be used for this problem. We do have to avoid that one. Let's count how many times is this iterating. I'm just going to add a count one to see how many times is this loop running. It should be running. How many times should it be running? 4, right? 4 divided by 0.1 should be running 40 times. Does that make sense? Because there's a 4 in between here, and it's going to be 0.1 as a width. So this should end up printing out 40, right? Does it print out 40? This one prints out 2, that's fine. Prints out 4, that's fine. That's not right. That's a 41. Rounding point errors, so we can fix this one of two ways. We can use epsilon, which is like a really small number, and say while x minus r is less than that small number. Does the count still work for this one? This one's going to fail because I still have the counts. Still going to be 41. I think is we would have to do a greater than. Now it's doing a 40. This is like the fancy way to do it. You could also do something like this. Int iterations is going to be right minus left divided that by the width. Round this one. We're just going to round to the nearest number because iterations might also be a floating point number.
I think you need an extra.
Well, iterations is bigger than 0. Something like that. Should still work. Both ways are fine, right? but that epsilon thing is the most standard one for fixing those running errors.
The way we did it is we rounded the x value to about 5 decimal positions, and that worked.
Okay, that also works. All right, nice. Team balance A. Now this is where it gets fun. This is actually a pretty famous problem. I think this one or team balance. Oh, I'm thinking of team balance B. Never mind. But how this one works is that we have a bunch of people here playing sports. I think soccer, right? Yeah, soccer. So we're pretty much trying to split this team to, and you're like, so these are all people on a team, and you want to practice. We don't want it to be unbalanced or also to be a sweep. So we want the teams to be as balanced as possible, so everyone's still having fun and learning something, just like this contest. But how this is going to work is that we're trying to find the optimal place to split it so that each team is most balanced as possible. Let's try to go through this one. 4, 2, 5, 1, 2. This whiteboard is pretty nice. This is my first time doing it on this fancy Windows 11. So 4, 2, 5, 1, 2. There are 4 possible places where we can split it. What if we just try all 4 of them? We could try to split it in between here, 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 or here. What? Let's say my left side is going to be on team 1, and my right side is going to be on team 2. If I split it here, how many people are going to be on team 1? Or what's the total power of the people on team 1? It's going to be just 4. On team 2, it's going to be 10 for 2 plus 5 plus 1 plus 2. Then we'll try the next one. What if we try a 4, 2, and a 5, 1, 2? That's going to be 6 and 8, right? And the next one is going to be, what is that, 11 and 3? Last one is going to be 12 and 2. But the question for me, from me is, what is the best way of computing these team values? How do I do the eraser? Oh, so while I'm struggling with this, how do you guys think, how do we get these values efficiently? What do you guys think? Perfect sum? We could do something similar. I like to think of this one more as an accumulation.
Yeah, I mean, like each time you split it again, you just remove one from the right team, add it to the left.
Exactly. Let's say we're going from, let's just say it's 4 and 10. It's going to be looking like this. If we split it like this, all we're pretty much doing is moving player 2 from team 2 to team 1. That means that team 1 is increased by this number, team 2 is decreased by this number. We can see a plus 2 in here and a minus 2 in here. Plus 5 in here, minus 5 in here. Plus 1 in here, minus 1 in here. Once we do this, all we need to do is take the minimum difference of these two. So 6 minus 8, sorry, 4 minus 10, 6 minus 8, 11 minus 3, 12 minus 2. Absolute value, that's going to be 6, 2, 8, and 10. And find what's the smallest difference we can get. Let's go to this one. Oops. This one is always so fun to code. The input array parse thingy. If we do that, let's start with it looking like this though. What if we just have a team where everything is on team 2? Because we split it like this. This is going to be our starting point. 0 and 14. How do we get this 14? What do you guys think? How do we get 14 from this array? Well, 4 plus 2 plus 5 plus 1 plus 2. It's going to be 14. So, team 1 is going to start off as 0. T2 is going to start off as sum of that array. And this is going to be O of n. There's no better complexity for sum. Not really, yeah. Sum is always going to be O of n, there's no better way. So we have to do this like this. I'm going to do like this. For I in range of the length. We're going to start off my best. What if my best is just going to be T2 to start off as? For I in range length. For each of these, for every iteration, I'm going to start by swapping the player at that index from team 2 to team 1, which is going to mean I'm going to subtract that value from T2. I'm going to add it to T1. So I'm going to do T2 minus equals array at I, T1 plus equals array I. Best. Every time I do that, I'm going to calculate the best again by doing the minimum of the current best and the absolute value of T1 minus T2. Note that even though I did T2 minus T1 here, since the absolute value, order is not going to matter down here. Before I print out the best, I'm going to print out T1, T2. Oops. Wow, holy cow. Let's see. If we do this one, we're going to start off as 4, 10, 6, 8, 11, 3, 12, 2, 14, 0. I did say in the constraints that we're gonna, each player must be put into a group. Each group must have at least one person. We can just stop the loop one iteration less by doing this. There we go. The minimum difference is going to be 2 and 6 and 8.
Will start increasing.
It will. As an optimization, you could just stop the loop as they pass each other, but or at least it becomes bigger than the max. But I don't know. Now, team balance A is a pretty interesting one because it's just O of n, a single pass, really double pass because you're using the sum. Team balance B is where the fun one is. Team balance B is a bitmask question. So I've told this joke like 1,000 times, but what do COVID? But what did binary numbers were during COVID? Bitmasks. How this one works is that now we are allowed to take subsets. We're allowed to split the team into sets. So you don't have to like keep the order of this one. I can pick my team 1 to be 2, 7, 3, and my team 2 to be 4, 1. I don't have to like split it right in the middle and put everything on the left to one team, everything on the right to the other team. So can somebody tell me, out of a subset, sorry, from a set of, wow, that's terrible, A, B, what are the possible subsets? A subset is just any combination of these ones.
There's 4 subsets.
4 subsets. Can someone give me the first subset? And don't go in order, just go through anyone. A, B. Just A? If we were just say I have to have just B, right? Just B? Yeah, A and B, yep. And of course, the empty set with nothing. Now, what if we have just A as a set? What are the possible subsets? There's 2 of them. Of course, the same set. I think the identical set is what the math nerds call it. And the empty set, which is also what the math nerds call it. Trivially, this empty set is just going to be this. I'm becoming Balaga, I'm saying trivial. Can somebody tell me then, without doing the calculation, how many subsets is possible if I have a set of A, B, C, D, E, F, 6 elements? If a set of 6 elements, how many subsets are there? Well, if I think of this one as 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, if I have a set with 64 with 6 elements, that's going to be 2 to the 6th. It's going to be 64, the Minecraft number. We can use this to advantage by thinking not in decimal, but in binary. Bitmask is a technique where we're treating this number as a binary number, and we're thinking if. And we're going to think like this. If, let's write it down first. How about we do that A and B? for I in range, and instead of I, I'm actually going to call this one mask, because it's cooler. Range of 2 to the power of length of the array.
Jason, I do have to go.
Sure, sounds good.
Sorry, but
Thanks for helping out. Contest went very well.
Yeah. Yeah, we should do more of these though. These
Yeah.
solutions. This is
Hey,
really
next to the
fun
club.
actually to watch these.
Yeah,
Yeah.
we'll do it
Okay.
later. We'll think about it later.
Okay,
Thanks for the help.
Yeah, of course. Thank you for coming.
For sure.
Thank you guys for coming too.
For every mask in this range, let's think of these masks in binary. Let's say this one. My mask for this one is going to be 0, 0, 1, 1, 0, and 1, 1. Or 0, 1, 2, and 3. This is the binary representation of it. And we could say, if I'm at a 0, and we're just going to go through each one of these numbers. If I'm at a 0, I'm going to add it to team 1. If I'm at a 1, I'm going to add it to team 2. So to actually convert the number to binary, there are 2 ways, the easy way and the fancy way. I'll show you guys the easy way. I'll show you guys the fancy way later. We can do bit string. It's pretty much the number in binary as a string equals bin of this mask. So if my mask is going to be 3, my bit string is going to be a string of 1, 1. Now we're going to do a for loop through this bit string. For I in range of the length of the bit string. We're going to do like this. Team 1 equals team 2 equals 0. Before this for loop, we're going to say if bit string at I is 0. Since this is a string, we'll have to use the string instead of an integer here. If it's a 0, how about we just add it to team 1? T1 plus equals, wow, it's bad. Team 1 plus or equals the, what do I call this array? S? S at I. We're adding the ith element to team 1 if there's a 0 there. Otherwise, if it's a 0, T2 plus or minus Si. We do have to be careful with this one, because when we do this, just like this, there's going to be some left over that aren't in any teams. If there are some that are left over, we can think of all of those as, we can think of all of those that are left over as zeros as well. So I'm going to rearrange this code to be like this. Oh, that's a ruler. How do I turn that off? I'm going to say, if I in range of length of the original array, we're going to do if, and just like before, we're going to get that bit string equals the binary. Uh-oh, did I do that already? Oh, bit string's up here already. Oops. I'm going to do if I is less than the length of the bit string, then we're going to do this. Otherwise, we're just going to add it to team 1. Because even though our binary numbers are like this, when we do the bit string, sometimes the length might be off. Sometimes it might be just 0 or just 1 instead of our standard 1, 0 or 1, 1. I do have to be careful for this one. Cooler way of doing this one, I prefer much more, is by using bit shift. Bit shift means pretty much you have a binary number and you're seeing, is that bit active? I'm going to erase this code, but it's going to have pretty much the same logic. How do I use this eraser? It keeps breaking. Oh. Oh, come on. Oh. There we go. Oh, that's too much. Okay. Give me some time. This is mostly new to me. I haven't done this in a year. So I'll move this on here. And it's going to go like this. 4. Bruh. For I in range of my length. And we're going to say, instead of a bit string, we're just going to use the mask directly. Oh, why doesn't this work? How does this eraser work? Okay, eraser, please. Everything in the length. I'm going to do, if that bit is active, by doing like this. If mask and, this is just one and. I'm guessing most of you guys haven't seen this before. One and is bitwise and. And I'll explain what that means in just a second. 1 shift I. Now that means the bit is active. We'll put it in team 2. Else, we'll put it in team 1. Just like before, we'll do that max code, but I'll do that later. How this works is, let's say my mask is like a 1 0 0 1 1 0 0 1 0. Sure. We're just gonna go through this. I is just gonna go through every element from 0, 1, 2, and 3, and it's gonna go like this. This shift means pretty much I have my 1 here, and I'm just adding a bunch of zeros on the left side. I'm pretty much just like pushing it, shifting it. To see if a bit is active, we need to use and. Let's say my I equals 1. So I shift it 1 time. 0, 1. Now we do the and. Bitwise and is going to do the end of these 2 bits, which means if they're both 1, then it's going to be a 1. Otherwise, it's going to be a 0. If this does end up being active, this result of the and is going to be positive. Otherwise, it's going to end up being 0. I put a 0 down here because it's going to be 0 down here. Even if there's like nothing after the binary number, you can think of them all zeros. If it's 0, that means it's not active, which is a 0 in the bit mask. Otherwise, it's going to be a 1. Let's get to coding this one. I'll show you how to do it on Python. Just like before, length, array, I hope this is recording correctly. Do 4 mask in range 2 to the power of length. First, this works. The cool guy version of doing this one is 1 shift by the length, because it's cooler. This is identical to 2 to the power of length. Because if you think about it, shifting to the left once by adding a 0 to the end in binary is just multiplying the power by 2. Multiplying by a power of 2. Doubling it pretty much. Then inside here, for I in range of length, we're going to do, full disclaimer, this algorithm is terrible for time complexity. This is O of n times 2 to the power of n. Very, very slow. But if we take a look at the constraints, we can say that it's totally fine to be brute forced, since the constraints are small enough that it works. So make sure to take a close look at the constraints. Make sure you say, look for the patterns. If it's small enough, you could try to brute force it. Otherwise, you'll have to look for a more efficient solution. If mask and 1 shift by I, if this ends up being greater than 0, we're going to add it to team 2. Else we're gonna add it to team 1. Like before, we're gonna do the best stuff. Let's see. I don't know. Which is at best as first? 1,000. I don't know. I choose 1,000 arbitrarily because it's just some random number. We're gonna be changing this best, so it's gonna be lower. We're looking for the best one. We're looking for the lowest one. This at the best is gonna end up being smaller. I have to be careful when I choose this 1,000 because it has to be bigger than this constraint. If it's less than 1,000, maybe I choose 100. Then this solution is not going to be 100, even though the solution for this one is 900. And let me show you guys what I mean by that by just giving an example. Best at minimum and absolute value of T1 minus T2. Same logic as the previous one. And we're going to do it like this. Let's see. Not going to work for this one because we're printing out 100 because of this best is best. Every possible combination is either going to be 900 is the only possible combination here. 1,000 minus 100. But that's bigger than 100, so 100 is chosen instead. We don't want to choose 100, so I'll choose 1,000 instead. Or crazily large number. Give it a try. I think there are like 2 more, maybe? Parity Sum? Okay, 3 more. Parity Sum, you can solve this one of 2 ways. How many of you guys solved it with math? Using the equations? Anyone? Where's everyone? Who solved it with the dynamic programming? Cool, we'll go through both ways. Okay. Parity Sum goes like this. I'm going to give you a number. I'm going to give you 100,000 numbers, actually. And we're going to say, if that number is even, then we're going to return the sum. We're going to return the sum of every even number that's less than or equal to it. Otherwise, if it's odd, we're going to return the sum of every odd number that's less than or equal to it. Greater than 0, of course. Very, very easy code for this one is just going to be a for loop, right? While the number is greater than 0, sum equals 0, sum plus or equals the in minus equal 2. Does this code make sense to you guys? While the number is bigger than 0, we're going to add that number to the sum and subtract 2 from the number. So it's going to, if my number starts at 7, it's going to be 7, 5, 3, 1. If my number is 10, I'm going to 10, 8, 6, 4, 2. That'll work. But since we have so many numbers here, the numbers can get so big, it will be slow. But the beauty of this one is that if I'm at a number that I've seen before, there's no reason to compute the next one if I can just save the previous results and use that previous results to compute the current results. That is a process called dynamic programming. And we can solve it one of 2 ways, tabulation or memoization. We'll solve a tabulation. We'll take a look at memoization in the next problem, buffet rate. But we'll solve it like this. I'm going to first start by making an array from 0 all the way to 1,000,001. The reason I choose 1,000,001 is because our numbers can get up to 1,000,000. And we need our indexes to be from 0 to 1,000,000. A very, very big array. I'm going to start it off as just a small one for now, just so we can, we'll get to the code later. How do I control Z? I'll just put it there for now. How about I call this one my lookup? 0, 1. And then we'll compute the rest. Let's see. And then I'm going to do a for loop for this one, all the way to 1,000,000. How this lookup table is going to work is that the element at index 1 is going to be the result for calling parity sum on this. The result at index 2 is going to be the result of the parity sum starting at number 2. The value at lookup at 100 is going to be the results for the parity sum at when your number is 100. Let's do it like this. For I in range 2, all the way to 1,000,000. The lookup, and we're just gonna, this is all pre-processing. We're gonna make the lookup first, and then we're gonna use this to solve the problem. Lookup at I is the lookup I minus 2 plus I. The logic is pretty much the same. Look at this. We're gonna add it there. Goes to the next one. Just like here. Add it here. This goes to the next one. It's just in a different format, pretty much. It's just like a different way of looking at the problem. At the very end, this lookup will be populated, and we'll be able to use this one to very, very easily solve the problem. Let's just go through some examples. How do I do the eraser on this one again? Next one is going to be 2, because that's going to be 2 plus 0. This one is going to be 3 is going to be 3 plus 1 is going to be 4. 4 plus 2 is going to be 6. That's going to be something. 9. 5, 6 is going to be 12. Then we'll use this lookup table to calculate the results by just looking at the lookup table and get that value. So let's make that lookup table. Do lookup at 1 is going to be 1. Then do the for loop. For I in range of 2. Lookup at I is going to be, let's see, lookup at I minus 2 plus I. Let's take a look. There it is. So at index 1 is going to be the result of parity sum if I give you a 1. If I go to index 3, it's going to be a 4. If I go to index 4, it's going to give me a 6. Index 5 is going to give me a 9. Index 6 is going to give me a 12. Index 7 is going to be a 16. Just like this one. All we need to do now, go through each one of these. Just get the elements at the index. Queries. We didn't even start the input parsing yet. We were able to pre-process this one before we even got any inputs. Print lookup at. Let's see it. That's awkward. Oops. No. Don't do what I did. Please check your code beforehand. Don't go submitting it. I was too overconfident for this one. Let's see. I'll go to this one. Any questions?
Couldn't you also do that with the equation for the sum of everything?
Yeah, totally. I totally forgot about that one. Let's go through it. Let's take a look at the sum for just the odd numbers. 1, 3, 5, 7, 9. It's going to be 1 plus 3 is going to be 1. 1 is going to be 1. 1 plus 3 is going to be 4. 1 plus 5 is going to be 9. 1, 3, 5, 7 is going to be 16. 1, 3, 5, 7, 9 is going to be 25. What pattern is this? Square numbers. 1 squared, 2 squared, 3 squared, 4 squared. Wow. How do we do Control Z on this computer? It's not working. 4 squared, 5 squared. Problem is, how do we get from these numbers to these ones? If we add 1 to the number, if we take this 9, 9 plus 1, and then divide it by 2, it'll give me a 5. So I'm going to do, if the number is odd, print that in plus 1 divided by 2 squared. Even is a bit tougher. Is a bit tougher. I don't know if you guys have seen this pattern. It becomes a bit easier, but it's still not as easy to see as the square ones. 2, 4, 6, 8, 10. It's gonna be 2, 4. 2 plus 4, 2 plus 4 plus 6. There's the reason I wrote this out is because I'm going to do this. Factor out the 2. 1 plus 2 plus 3. There's never just one way to solve a problem, hopefully. Do you recognize this pattern? These are the triangular numbers, these are. It's a very interesting sequence as well. These, there is a formula for triangular numbers. If you would do n times n plus 1 divided by 2. Let's say my n is like let's say my n is 3. Let's say I just have a 3. 3 times 4 over 2 is going to give me 6. Okay, so the sum of this one is going to be 6. 4 plus 5 over 2 is going to be 20 over 2, which is going to be 10. Just like this. Once again, the problem is actually getting this number, this 4, this element number. We want to be able to map 2 to 1, 4 to 2, 6 to 3. Oh, that's not bad at all, actually. We just divided by 2. Huh?
You divide by 2 on the right, but then you multiply by 2 on the left.
Yeah, so on this question, these will cancel out. This will be the solution. Problem is actually getting the in. In this case is going to be the input divided by 2. 6 is going to go to 3, 8 is going to go to 4, 10 is going to go to 5. This solution is, I will say, a better solution because it uses no extra memory. Memory may also be a constraint that you have to take note of in some challenges. So, O of 1 time for each one, and it's also O of 1 space for each one. So, good solution. Want to see if I can do it on one line? Let's see. I don't know. I don't think so. Print, we're going to do n to the... Yeah, ternary I'm thinking of. To the power of 2 if n we're going to do n over 2 times n plus 1 over 2. Does this work? I swear if this works, that'd be really funny. Let's give it a try. Yeah, it's Python. Oh, okay. Let's see. If let's see, like this. Does this work? Oh, okay. Well, that's silly. It's pretty much something. I just run everything by.
Oh.
You found it?
In that middle statement, it's doing the modulus of 2.
Gotcha. Okay, I understand.
And assigning that.
I see. Good catch. Thank you. Oh, this works, right? Oh, okay. So almost there. It's running into a bit of a problem here. N plus 1 divided by 2 times the power of 2. I don't know. Well, you guys get the idea, right? You can use math to solve this one?
Yeah, this is the problem with writing things from one line.
Yeah, exactly.
It's impossible to do that.
Right. So I'm going to do n equals I'm gonna do if in modulo 2 equals 0. So if it's an even number, I'm gonna do in equals in divided by 2, or I'm just gonna do 2. Do print in times in plus 1. But if it's odd, I'm gonna do in equals in plus 1 divided by 2, print in squared. There we go. Same logic, but not in a one-liner. This is a better solution than the array one, just because it takes up less space and memory, but time complexity is exactly the same. Still going to be O of n, since we're going to go through every single input. 2 more to go. Factor mashup, one of my favorites, besides buffet of course. Factor mashup is a 2-part problem. We need to figure out prime factorization and a breadth first search for finding this final array. Let's start with a prime factorization algorithm. Do you guys have any idea how to do the prime factorization? If we have a 12, 12 is not a great example because there are only 3 factors of it. Well, let's do a 300. We can just start by trying to divide every single number we can. So 300, we're going to try to divide it 2. Divide it 2 again. And then we're going to go up to a 3. We're going to go up to a 5. So prime factorization for this one's going to be 2 squared times 3 times 5. We're not looking for, yeah, exactly, squared, thank you. We're not looking for the prime factorization though. If we read this problem, it's going to be just the prime factors, but not the prime factorization. So just a set of 2, 3, and 5. How to write this algorithm? Do you guys know? Bit of a tough one. Let's take a look together. Find factors. Factors is going to be results. It's going to be some list. I'm going to do I is going to be 2. Then that's res. If res modulo I equals 0, we're just going through every possible number. We're going to try 2, 3, 4, 5, 6, 7 until we get to the point where we cannot divide it anymore. I plus plus, O plus equals 1, do if I. That's fine. I prefer, yeah, I could. In this case, I am going to make it a list, but set totally works. Just up to personal, for this problem, up to personal preference. Depends on the problem, of course. This one is fine. Yeah, that's true. But I'm going to do something different than that. I'm just going to use this list to generate everything. I'm not going to check these subsets at all. So but you'll see, you'll see. Let's try to print out the factors of 300. Let's do oh, oops. What? What is going on here? Oh, there it is. Thank you. Oh. There we go. Come on, work. Probably. If I forgot to do something. It's going this long, I maybe did a dead loop somewhere. Yeah, okay, let's see. I plus equals I did this one. Ah, that's why. Okay, there we go. That's like the 5th try, right? Okay, there we go. 2, 3, 5. 5? Only 5. I put it at 12. Oh, right. Let's do the input. Oops. Molding. Okay, let's try again. That's it. 2 for 12? Bruh. That's not right either. Let's see. That should work. 2, 3, 2, 5, and nothing. It should be 23. I didn't account for this one, just because. Oof. Let's see. Elif, or if that res length of that res is 0, that means it's a prime number. Res return that original number, pretty much. Yeah, because it has no factors, it's a prime number. There we go. Okay, that's fine. Is 260 really just a bunch of 2s and 5s? Can't be right, is it? $130, 65. Should be have a 13 in here as well. Let's see. I'm molding. If in is bigger than 1, then res.append in. Please work. 2, 3, 23, 2, 5, 13. Okay, finally. I think it worked. All right, that took too long. How's my battery life looking? 11. Is there a thing I can plug this in somewhere? I'll be right back. Does this reach?
Hopefully.
I don't think it does. That's not good. Let's see.
Will you do it in time?
Let's see if I go fast. I'm gonna unplug something that's gonna break. Oh, that's a protector. Let's see. Yeah, exactly. Short circuits and everything fizzes out.
You're gonna have to go to the breaker room.
Exactly. Yeah, all good now. Glad I caught. Holy, that's huh? It's a 5 now? Okay. Well, I'm glad I plugged it in. That would be really bad. Okay, so factor is there. All right, now some for the breadth first search. Yeah.
Peter gave me that your battery's about to die.
Right.
5 seconds later.
Oh no.
Didn't give me time to save the video.
Oh, that's the worst.
5 seconds.
That's rough, yeah.
Actually, I did save the video, just not the
Hmm.
audio. So it's
Right. That's annoying. All right, barbecue. What's it called? Barbecue fish sticks algorithm. Breadth first search, or barbecue fish sticks. I was gonna make that the name of my ICPC team this year, but we'll see. We'll discuss with the team. How this is gonna work is that I'm gonna have like a node. This node I'm gonna start it off as 1. For everything inside this one, I'm gonna try to multiply 2. Try to multiply 3. Multiply 2. Multiply 3. Multiply 2. Multiply 3. Same here. 12. 12. 18. It's going to go out of bounds. We're going to ignore that one. 12. And it's going to be 18 again. And it's going to be 18 and 27. All these ones are going to be out of bounds. All that's left is going to be the result, which is going to be 2, 3, 4, 6, 9, oops, 8, 9, and 12. To code this algorithm, I'm going to first start with an array called cur. It's going to start off with just as a 1. And I'm going to say for each of these ones in here, I'm going to try to multiply by 2, multiply by 3, add it to my next array, which is going to be 2 and 3. Same process here. I'm going to end up with a 4, 6, and a 9. I'm going to do, if I've seen one already, I'm not going to re-add it to the array just to save some time. And the very end of this one is going to be 8 and 12. If it goes over that 12, because it's the limit, I'm going to stop. To code this one, I'm going to do like this. F equals vectors. How many parentheses do I have here? Okay, let's do it like this. My cur is going to be my current array. I'm going to start it off as 1. Seen is going to be, which ones have I seen before? Seen is going to be a set. Then I'm going to do my BFS. While my cur is, while I still have things in the cur, next, I'm going to do like this. For everything inside cur, for everything inside the effects, or in for number, for everything inside the factor, I'm going to do result is going to be in times the factor. I'm going to do if my res is in the scene, I'm going to do nothing. If I've seen it already, there's no point in putting it there again. There's no point in calculating it again. Then I'm going to do, if it's not in scene though, we're going to do next dot append res and scene dot add res. At the very end, we need to set cur is going to be next. Print sorted scene. Let's take a look. Scene is going to keep track of which ones I've seen before, pretty much. At the very end, that scene is going to be at the very end, scene is going to be all of the elements I've reached using that breadth first search. Yeah, what's going on here? Res is going to be in times f. What? Memory error? What's going on here? Huh, I've never seen that before.
Means something's expanding quite big.
Apparently.
Are you multiplying a list?
Nah, in should be my current number. F should be my factorial. I'm going to try to print in an F. I've never seen this before. I don't know. Oh, oops. Or res bigger than 12. There we go. That shouldn't crash the program now.
Not 12, it should be the.
Oh yeah, that's true. The starting number. I'm gonna call this one like limit, I guess. I don't know. I was scuffed. Okay, there was all the numbers. All that's left to do is to format it. To do that, we can use another map. We need to join this all together. If we do just a join like this, it's not going to work since all of these ones are integers. We can't join integers. We have to map these ones into strings first. What?
You gotta add a space.
Oh, that's right, yeah. There we go.
There you go.
That took me too long. Wow, that was silly. How's my battery life looking? 7? Okay, that's right, it's too slowly.
When we did that, we used a different algorithm for it.
Yep.
Because I guess we were trying to get fast. And
Can I take a look?
Sure.
All right.
We got some of them right. The others timed out because we used a different algorithm.
I see, okay.
We
Let's
were
see.
full in-
Let's see. Is it we're looking for a what's it called? Parity sum or factor mashup? Look here. Was it this one? Someone
Yeah.
else?
We got 2.4.
Oh, okay, there we go. Nice.
That's what I mean by the is subset thing.
Gotcha. I see. Oh, I see what you did. Yeah.
We did kind of brute force style.
Yeah, brute force style for sure.
Which
I see.
timed out later on.
Which yeah, that does time out unfortunately. I want to see what are the constraints for this one. I can't see. Remember. The fifth. Oh,
Yeah.
Hmm.
Doing brute force on all of those numbers,
that's tough. Yeah.
and then finding factors of all of those numbers.
Right. That's gonna be a killer for time.
Uh,
Fair raid. Some of my favorites.
did anyone even attempt this?
The speedrunner at Davis did, but I don't think so. Not here. Someone attempted it once. I wonder who it is. I think Nick did.
Oh, a few people.
Yeah, Nick tried it.
What are they?
Ray is the guy at Davis. I've attempted it 3 times. There's me and Lego. But how this one goes, this is a dynamic programming question. Have you heard of dynamic programming? It's one of my favorite techniques ever. Dynamic programming is using the results, and I went over a little bit when we were doing parity sum with the array version. That's a form of dynamic programming called tabulation. Now we're going to do one called memoization. 2 different ways to do it. We're going to do this one recursively. In most kinds of dynamic programming, you could do it iteratively, but recursion's cool, so I prefer recursion. But we're going to do it like this.
That isn't until you get a Stack Overflow.
Right.
Too many stack frames.
True. That's how it would be. All right. So let's say my 1, 4, 2, 1, 5, 1, 7. What's that? Maybe. That's going to be my input list. And we're looking for how much food I can eat when I can only eat up to 2 in a row. So I can eat 4 and 2, but I can't eat this one or this one if I have these 2. Or if I eat 5, I can like skip to these ones by skipping 1. But if I decide to eat, oh wow.
Life would be so much easier if you could just eat all.
Exactly, right? But unfortunately, you get kicked out of the buffet. That's the story. So you can't eat too much food, or else you get kicked out of the buffet. All right, let's see. Technique for this one is, once again, when you're doing a problem, it's great to just draw it out beforehand, to see how you can think of it as a person, and then implement it with code. So don't jump straight into coding. Rather, you should start by drawing it out, drawing diagram, and then begin with the code. Let's start with 4. Sorry, let's start with 0, 1, 2, 3, 4, 5, 6. I'm gonna call this my function of I, and I'm gonna do it like this. 0 is my starting point. When I'm at this starting point, we can think of this one as a decision tree. What choices can I make when I'm at 0? When I'm at 0, I can either eat 1 food or 2 foods. I can either eat just this one or I can eat just these 2. Which means I can either, and so if I decide to eat just 1, I have to go to 2. Or alternatively, I can skip this one and just go to the next food. So my 3 choices are, wow. Choices: eat 1, eat 2, or skip. If I decide to eat 1 food, that's the equivalent of adding this element, and then I have to go to 2 because I have to skip the next one. Does that make sense? I can't eat 2 foods in a row, so I can't eat 3 foods in a row, so I have to skip the next one, go to 2. If I decide to eat this 4 as well, I have to jump all the way to 3. But if I decide to eat none of them, and I can just skip this one, just go straight to 2. So I can either do my array at 0 plus function of 2, array at 0 plus array at 1 plus function of 3. say these two, skip to 3. Or I can skip right to function of 1. How do we code this is the harder part. I prefer to do this one recursively because recursion is cool. So let me take a look at this one in the code editor. I'm going to make my function. Are you guys in serial math? Do you take math courses here? The head honcho of math here, the big cheese, his name is Dan Balagai. He's quite a character. I think he, I don't know if it was him or some of his students who started the saying, state the answer, which means you instantly have the answer without thinking about it. I've started to write my functions as STA, standing for state the answer. You can name this function anything you want. F is standard for functions, I think. You can also like a foo or go, define go, or define foo, define F. I prefer STA because it's funny. 3 choices we can make here is eat 1, which is going to be, and of course we should actually get the array first. 1 final array parse for today.
One line there is one of the most commonly used lines in these computations.
Oh yeah, for sure. And heck, we can even do these in one line if we just do a little funny. Eat 1 is a choice to say if I decide to eat the very first food. If I decide to eat the food at element I would have to go to the function of I plus 2. Eat 2 foods is if I decide to eat the array at I plus 1, I plus 3. Or if I just skip it, state the answer of I plus 1. At the very end, we have to return the maximum of eat 1, eat 2, eat 3. Or skip, I mean. All I need to do now is to print STA of 0. I start on 0 and we say, what are the choices I can make that leads me to the most amount of food I can eat? By itself, this function is going to completely break because I still have to add an important part of this function, which is the base case. The base case says, if I'm at a point where I can recurse no further, instead of crashing, I have to stop recursing. It's going to be like this. If my I greater than equal to length, return 0. Not every question is going to look like this. It might be if I is less than 0, or if I reaches a certain point, and I might not return 0 every time. I might return a 1. Maybe I'll return infinity. In this case, I have to return a 0. By infinity, I mean arbitrarily a large number, which I will use. Maybe. We're also going to do like this. We're also going to compute eat 2 if that I plus 1 is still in bounds. This has the potential to go over the length of the array. We're going to do if I is less than, I plus 1 is less than length, only then can we compute eat 2. Otherwise, eat 2 would be infinity. The reason we do this one, wait, infinity is not right. We should do like a negative infinity. Something like that. 0.
Negative 187 or
something like that, yeah, just some value. Since we're looking for maximum, if I do infinity here, it's going to select that every time. But if I do a 0 here, it's like never going to select it. It's always going to select something equal to 0 or bigger than 0. Pretty much just eliminating eat 2 because we cannot select it. There's no way to eat out of bounds of the array, pretty much. That's it. Perfect. Does it work?
That one looks so simple.
Is it simple? It's not going to work. Not yet. We have to make one more optimization.
Oh yeah, because that's going to cause a lot of recursion.
Yeah. So let's think about it like this. every time I call f of 0, I'm calling f of 2, 1, and 3. So 0 is going to be calling 1, 2, 3. 1 is calling 2, 3, 4. 2 is calling 3, 4, 5. 3 is calling 4, 5, 6. But when I get to this 3, we can... Okay, when I get to this 2, we compute all of these ones. I get to this 2, but I've already seen that 2 before. Every time I call function of 2, it's going to give me the same exact result every time. There's no point in computing that, going through that recursion tree, if I already know what I'm going to get. If I can save the value from here and just return that value up here, then we can speed this up to only O of n time. Like here, I think this is O of n cubed, just because you have to split into 3 every, or sorry, O of 3 to the n. We can split that up a lot if we do the memoization. For this one, I'm going to use a lookup table, just like I did with Parity Sum. I'm going to start it off as -1s for, let's see, length. And I'm going to do it like this. If I've seen it already, that means my lookup at that index is not -1. If lookup at I is not -1, return that value. But otherwise, if we haven't seen the value before, we need to run the computation. Result equals that maximum. We're going to save that result into the lookup. And then return that result. That's it. Optimization, baby. Let's see the O of n time. And that's buffet raid. Look at that.
Man, I can't wait to take some college level programming classes to learn some of this stuff.
This isn't taught in under division courses. You have to wait until upper division courses. I really do hope that you go on LeetCode on HackerRank and do some of these on your own, because this stuff like this is not going to be taught at our at the undergrad, at the lower division level. And even when you guys the upper grad level, the class I'm taking, the algorithms course, it's all just theory. You don't really learn how to do this in practice. So do take a look at these ones on your own. Do the code, go through the problems. Just get the feel of it, get the practice of it. That's all the problems. Do you guys have any questions on that? All set then, okay. That's all of these, SCP-3. I will stop the stream. Thank you for watching, buddies. And how do I stop the stream? I'm gonna click on this button. All right, thanks for watching. Do these problems, and I will see you later.